It's a great pleasure to talk at the Appleton Conference about Solar Orbiter. It's a joint ESA-NASA mission to study the Sun, the heliosphere, and the connections between them. The roots of this mission can be traced to a meeting in 1997 when a small group that included RAL Space proposed the concept of Solar Orbiter. A formal proposal was submitted to ESA in 2000, and 10 years later, when funding became available on both sides of the Atlantic, the work on instrument hardware began. The contract to build the spacecraft was awarded to Airbus, and the instruments were delivered to Stevenage in 2017. Solar Orbiter was launched on the 10th of February last year. This was followed by 4 months of commissioning activities. Instruments were switched on, testing all subsystems, getting first light and more data during the first perihelion at half the Sun-Earth distance. This was followed by an 18-month cruise with more tests and more observations. The cruise ended 5 days ago, and we are officially in the nominal phase of the mission, ready for science. The first close perihelion will take place in March next year. The planets on this movie are Earth, Venus, and Mercury. The goal is to get close to the Sun, 42 million kilometers at the closest approach. This will take the spacecraft inside the orbit of Mercury. To get this close, we need several planetary flybys with Venus and Earth. The Earth flyby took place on 27th November. The spacecraft flew at 460 kilometers above the Earth. It had to cut through the geostationary orbit and fly along the low Earth orbits. They are populated with thousands of space debris, so this was considered a risk. The final calculation gave a very low probability of collision, and the spacecraft did make it safely, and it's now heading towards the Sun. The payload consists of 10 instruments. The 4 in situ instruments are located on the long boom. They measure the plasma in the solar wind, elements of the solar wind, protons, electrons, heavy ions, magnetic fields, radio and plasma waves, and energetic particles. The remaining 6 telescopes are hiding behind the heat shield, and they observe the Sun from a distance at wavelengths across the electromagnetic spectrum, from visible light, extreme ultraviolet emission, and X-rays. This is a highly international project. 8 countries leading the instruments are listed on this slide, but there are many more groups with several other countries contributing many subsystems to all instruments. I want to emphasize the role of the UK. First, Airbus UK built the spacecraft, and that's a tremendous achievement. We have 4 instruments with contributions from groups at Imperial College, UCL MSSL, and STFC. 2 of the instruments are led by UK principal investigators, and on 2 others we have co-PI roles. RAL Space led SPICE Instrument Hardware Consortium for 8 years. To show the results, I will be moving from the surface into the extended corona and to the spacecraft. The first instrument is PHI, Polarimetric and Helioseismic Imager. It has 2 telescopes. It measures velocities on the surface of the Sun. These velocities on the left oscillate due to the sound waves traveling inside the Sun. The Fourier spectra on the right show these beautiful ridges with many frequencies. This area of research is called helioseismology. We can reveal structure of the Sun inside, flows under the surface, and understand the working of the solar dynamo, which generates magnetic fields inside the sun. So Phi has another telescope that records the magnetic fields on the surface. It measures the full disk, where the green and yellow are two magnetic polarities, and also has a high-resolution field of view. This time, black and white are small magnetic fields in the quiet sun area. These fields spread around the sun in three-dimensional space, creating magnetic loops, and they are extremely important. They drive and control all activity in the sun's atmosphere. So these loops are filled with hot ionized plasmas, which emits copious amounts of extreme ultraviolet radiation and some X-rays. EUI is an extreme ultraviolet imager with several telescopes. It has one full disk telescope with two channels. The orange sun is plasmas at 50,000 Kelvin. The yellow sun is 1 million Kelvin corona, and the high resolution is shown in purple. The typical sun at the beginning of the solar cycle is like shown here. Quiet sun with maybe one or two active regions and a large coronal hole at the top, which is the source of the fast solar wind. And EUI can catch anything on the sun, whether that is large eruptions or very tiny explosions called campfires. Another instrument observing the atmosphere in extreme ultraviolet wavelength is the SPICE spectrometer. It stands for Spectral Investigation of Coronal Environment. As I mentioned earlier, it was built at RAL Space. We led a large international consortium of 11 groups from 6 countries. SPICE has a smaller field of view and provides spectroscopy on parts of the solar disk and near-sun corona. And it's a special, unique instrument on solar orbiter because it has a diffraction grating that splits EUV light into individual wavelengths. This spectrum in 2 bands is shown here in the middle. The peaks are the narrow emission lines. They are emitted from a range of temperatures, from 20,000 to over 1 million and 10 million in flares. The labels above those lines tell us that there are the same elements on the sun as we have on Earth: hydrogen, carbon, oxygen, nitrogen, neon, magnesium, sulfur, and iron. SPICE can also measure velocities, and its mirror can be moved sideways to sample adjacent areas on the sun and build 2-dimensional images, as we see here on the left. Our immediate response to the campfires reported by the EUI was a discovery of beacons low in the sun's atmosphere. These are very bright sources and compact, up to 25 times brighter than average quiet sun around them. One of them is shown inside the yellow circle, and it can be seen in every panel near the center. We are excited about them. They are new. They can tell us new things about heating by compressed plasmas. Spacecraft can also repoint to the limb. That allows SPICE and high-resolution fields of view of EUI and Phi to study polar regions, in particular coronal holes, to understand the sources of the solar wind. The next instrument is Styx. It provides imaging spectroscopy of X-ray emission. It observes the whole disk of the sun, observing flares in X-rays. Since January, they recorded 3,000 flares. They are mostly very small, class A and B, because the sun is not very active yet. But on the 28th of October, we had a huge X1 flare, which is shown on the right from the SDO observatory. This is the white flash in the center of the movie. And the Styx image is shown as yellow and red blobs on the blue background. This arises from electrons impinging on the chromosphere and heating the dense plasmas to temperatures of 25 million Kelvin and more. The effect of this magnitude definitely had a big effect on the entire heliosphere. Moving further out into a more tenuous corona, we need to use an occulting disk that blocks the light from the entire disk. This is done by a Metis coronagraph. It observes in two channels, invisible light and an ultraviolet line of hydrogen. At the beginning of the year, they recorded these streamers in the equatorial plane of the sun. This is typical long-lived structures. But they are preparing to observe so-called coronal mass ejections. And the movie explains what they are. This is taken by a veteran of space, Soho-Lasko coronagraph several years ago during the maximum of the solar cycle. They are explosions carrying out billions of tons of matter at speeds between hundreds and 2,000 kilometers per second. They are launched in all directions and grow huge in volume as they move away from the sun. So Metis is preparing to observe them during the next encounters with the sun. The last of the large telescopes is a Solo High. It's a heliospheric imager observing in the visible light. It is pointed to one side of the sun to observe the sky. It can see stars, planets, an occasional comet, but all these lovely features have to be removed to reveal nearly empty space, just with the faint solar wind and sometimes a coronal mass ejections traveling from the sun. The snapshots on the left show how the shape of the mass ejection changes, how complex it becomes due to the magnetic fields. And these mass ejections are studied by heliospheric images on the STEREO mission, and a large amount of scientists is involved in this effort. So these mass ejections, solar wind and particles get to the spacecraft. There, the 4 in situ instrument observe continuously. MAG is a magnetometer measuring vector magnetic fields locally. It recorded the passage of a coronal mass ejections in the top plot, where the black curve jumps by an order of magnitude and other components change rapidly. It also measures at other times global structures of magnetic fields, waves, turbulence. It's a very precise, extremely important instrument. RPW is a radio and plasma waves instrument. It managed to record the radio burst during that large X1 flare. The plot at the top, the orange and yellow shape, is the signature of that radio burst, apparently the largest ever. At quieter times, it measures waves as shown lower. They affect electrons in the solar wind. SWA is a solar wind analyzer comprising 3 subsystems: electron system, proton alpha particles, and heavy ion sensors. The heavy ions come from the same elements as measured by SPICE, so we have here a potential to compare these plasmas. SWA measures the velocity in the solar wind, changing from the slow wind to fast wind on the left. It measures shocks when the mass ejections pass across the spacecraft, as shown on the right. It's a very comprehensive suite of instruments studying all properties of the bulk of the solar wind. But finally, the energetic particle detector, EPD, measures protons, electrons, and heavy ions that are 30 times to 1 or even 10,000 times higher energy than the solar wind. Such energetic particles can only come from cataclysmic events such as flares or CME shocks. And at the top we see a passage of protons across the spacecraft with very fine time resolution and very fine structure. This instrument also separates all elements into individual ions and elements. To connect the observations from the spacecraft to the surface of the Sun, we have to track back the parcels of plasma along the magnetic fields to the surface. The blue cross shows the connection point on that particular day, falling on the boundary between the quiet Sun and the polar coronal hole. On other days, it could be connected somewhere else, for example, to an active region. So that brings me to a summary of our science goals. We want to understand how the solar wind accelerates and where it originates, how mass eruptions affect the plasmas in the heliosphere, how are energetic particles accelerated, and how does the solar dynamo generate magnetic fields inside the Sun. And this is how we will do it. The spacecraft returns to the Sun every 6 to 5 months. When it gets close to the Sun grows large, and the telescopes start taking data for 30 days during each close approach. Then they switch to a low-rate mode. And we have 16 orbits like this from March 22 to August 2029. Finally, I want to congratulate the entire Solar Orbiter team for superb spacecraft and instruments, for successful launch and operations. Let's wish them luck and many great scientific discoveries. Go Solar Orbiter! Thank you.